Good morning. Let's start with a movie. And the cast of characters in the movie is a little bit complicated. So let me just run through the list of people you're going to see. Over here is the concentration of carbon dioxide in our atmosphere. These units are in parts per million, not much. On this axis here, you're going to see a place on the Earth, North Pole, South Pole, equator. And this red spot is very important. It's a site on the island of Hawaii, and it represents a place where carbon dioxide concentrations have been measured for some decades now. And then each one of these points represents a place on the planet at which that measurement of carbon dioxide was made. On this axis, same thing, concentration of CO2 in the air, part per million, and here is the calendar year. And so this is going to run. This clock will run from 1979 until 2016. And then the clock's going to run backwards about 1 million years. So that's what the movie looks like. Shall we do it? Okay, here we go. So first of all, you'll notice that the concentration of CO2 in Hawaii goes up and down. That's this red curve here. The concentration of CO2 in the South Pole also goes up and down, and it goes up and down exactly out of phase with the CO2 in Hawaii. You'll notice that the level, average level across the planet is rising. That's also indicated by this climb. And you'll also see there's a lot of noise, right? And as new stations come online, these things spike up and down. So any one measurement in any one time might not be very helpful in capturing the trend. The trend line, I think, should be pretty clear to all of you. This is going to 2016. This will be come up to about 400 parts per million. Today's value is 413, which I'll come back to in just a few minutes. Now we're going to go back in time to the 1950s and the same measurement from the Hawaii site. And now we're going to jump and use ice cores. I'll explain how we get this information later. And we're going to go back in time to about the year 0. And then we're going to look at a different set of ice cores and start going back in time about 1 million years. Remember, here's where we are today, and we're going back in time. And you'll notice that the concentration of CO2 in the atmosphere fluctuates quite a bit. It goes up and it goes down. These are associated with ice ages. Here we are today. Here's 1 million years. We'll come back and look at what happened 55 million years ago later in the talk. I just want to point out that the data obtained in this movie comes from a number of different labs from throughout the world. Some of these laboratories are from countries that are friendly to the United States, and some that are maybe less friendly to the United States. Oops, wrong button, excuse me. Okay, so why is this going up? And this curve, which began in the island of Hawaii, is due largely to Dave Keeling, who died just a couple of years ago. This curve is so important it was given a name. It's called the Keeling Curve after Dave Keeling. And the hypothesis is as follows. The reason CO2 is going up is because humans are burning stuff. Well, if that's the case, then we can employ some very simple chemistry to ask the following question. If fuels like coal and natural gas and the things in our car are burning to produce CO2, then we must be consuming oxygen. That's what elementary chemistry would say to us. And it was Dave's son, Ralph, who took up the charge of measuring the decreasing concentration of CO2 in the atmosphere. And here's a graph such as this right here. Now, you're going to ask me, is this graph going up and this graph going down consistent with the stoichiometry in this? And the answer is no. And so okay, let's deny this. This is not true. But actually, Ralph's major intellectual contribution to the field was not the measurement, but in fact, his insightful calculations as to how much CO2 was going in the ocean and how much CO2 was being taken up on land. And when you estimate those with the best tools of science, then the stoichiometry matches. That is, we're increasing CO2 because we're burning stuff. So how do we imagine that on a more local scale? So let's go to the eastern part of Germany, to a town called Jenswald over here. And there's a power station there. It is one of Germany's engineering marvels. It's a 3 gigawatt power plant. I just want to remind you that while we all herald Germany's leadership in the area of alternative energy, about a quarter of Germany's power still comes from burning coal. And the Jefferey power plant is one of the beacons of that particular process. So how much CO2 comes from this one coal-fired power plant? Well, we can do some calculations. It's a 3 gigawatt power plant. That's 3,000 megajoules per second, for those of you interested in those kind of technical details. And we know how much energy is associated from burning coal. We can measure that. We can look at the efficiency of the plant. We can do some other unit conversions. And we decide that the Jefferey power station consumes 25,000 tons of coal a day. So let's put that in perspective. These are big numbers. What that means is that that power plant consumes 218 railroad cars worth of coal per day. And when it's operating, that would be 24/7. All right, so how much CO2 comes from that? Well, we can do the same calculation. We know the stoichiometry. I showed you that earlier of how CO2 combusts. We do some unit conversions, and we come up with 3,000 cubic meters per second of exhaust gas from this one coal-fired power plant. Also a big number. So when you think about large volumes of warm, wet gas, you ask, how could I measure that? Well, here's a convenient way to imagine it. We can go to the internet and we can discern that the Trump Tower has a volume of about 300,000 cubic meters, which means the Jefferey power plant would fill the Trump Tower every 92 seconds with exhaust gas. 12% of that is CO2. That's one coal-fired power plant. Let's take a look at a more global perspective. In the year 2017, how much CO2 was emitted into the atmosphere just from coal? No cars, nothing else, just coal. And the answer is 1,400 million tons of CO2 into the atmosphere just from coal-fired power plants. Now let's put that in perspective. According to the plastics industry in that same year, the world produced 344 million tons of plastic. That is to say, by weight, we put 4 times as much carbon into the atmosphere as we did in all of our plastic products. That's why the atmosphere is changing. We're burning a lot, and that contributes to carbon in the atmosphere. So our atmosphere is changing. It's due to us, and the atmosphere has become our receptacle for carbon waste. So how does the Earth respond to this large change in the atmosphere? So the way to imagine that is we have to introduce a kind of wonky technical concept called a variance spectrum. And I'll illustrate it first with our bodies, and then we'll look at the atmosphere. So imagine your body as an object, and you're going to keep track of its mass. And on this axis, I'm going to put the change in my body mass. And on this axis, an event that occurs and the time scale of that event. So for example, at the time scale of 1/3 of a day, there's a peak because I eat 3 meals a day. There's a time scale on the order of once a day in which my body mass changes. We won't go into details. If I was a better person than I am, I would go to the gym every other day, and because of respiration and so forth, there would be a peak every 2 days. That's the variance spectrum of a typical human body. So what is the variance spectrum of CO2 in the atmosphere? This is what it looks like. This is the time scale. It's a log-log plot, so it's a little bit messy. So there are various peaks on that, and these are the way in which the planet Earth responds to changing CO2 in the atmosphere. So for example, what is this peak? It happens every day. That's the time scale. That's photosynthesis. Plants take up CO2 in the sunshine, and they grow. Here's something on the order of a year, and these are those oscillations that we saw in the Keeling Curve. Do you remember these wiggles? Well, the wiggles correspond to decreasing CO2 in the summertime because the plants are taking up, and increasing CO2 in the wintertime as a plant mass decays. And you'll notice the beginning of the year and the end of the year differ by about 3 parts per million. And that's our contribution to the changing atmosphere. So what about these peaks here? So there's a number of small peaks, and there's a lot of things happening on those time scales. So how do we discern those? This has to do with these ice cores. It's really a remarkable memory map of the atmosphere. You go to a place like the Arctic or Antarctic, and you drill down into the ice. So way back in time, snow fell, and that snow entrained the local air. And then the next snow came, and then the next snow came, and the next snow came. And so you have a tube in which you go back in time as you go down the tube. And chemists have been able to go to these ice cores and sample the air that was present for many, many thousands of years, in fact, even on the order of millions of years. And this shows one particular team in one of the more famous ice core samples in a Russian station, Vostok, in Antarctica. So that's how you get the data going back, for example, 800,000 years. It now goes back 1 million years just from those samples. And so what's going on there? Well, there are changes in the Earth's orbit around the sun. There are various kinds of fluctuations. But the biggest one is still sort of a mystery. It's believed to be associated with the circulation of the oceans. It is hypothesized that a large bolus of CO2 is carried in the currents under the ocean, and every 10 to 100,000 years, those deep currents come near the surface, CO2 goes into the atmosphere, the planet warms, algae grows, the algae grows in the ocean, and it sinks to the bottom and is carried by the river, a so-called biological pump. That's one of the interesting challenges in geochemistry and geology, is to discern all the details of these peaks. So here's a very big peak. It tails off, and it's on the order of millions of years. So what's happening on the order of millions of years that's moving CO2 through the atmosphere? So this is a complicated process, and as you can imagine, because it's geological, it's slow. But it starts with rain and CO2 in the atmosphere producing carbamic acid, not unlike the soda stream that you have in your home and the soda that I was so kindly given today. So that carbamic acid then dissolves rock and delivers to the ocean bicarbonate, calcium and silicon ions, which are taken up by plants, and they sink to the bottom. So what happens then? Those plants on the bottom are subducted at tectonic plates. They go deep into the earth where it gets very hot. And the reverse chemistry happens. CO2 is released and silicate binds. The CO2 comes up as volcanism and goes back into the air. So you have this huge cycle that involves many different kinds of chemical processes. And here's the important detail that's going to come back to us over and over again, which is how big are the reservoirs of carbon associated with all of these. So let's just make this the unit 1, whatever unit you like, we'll call it 1. And if you look at how much CO2 is in the oceans, it's 50 times, 100,000 times on the near surface, and 5 million times underground, which is to say whatever we do up here will be equilibrated with these species down here over geological times. I'll come back to this again later in the talk, but the good news is no matter what we do to the atmosphere, on the order of 100,000 to 1 million years, it's back to where it was. So here's our peaks. Here's the measurements that we were talking about before, and you might ask, where are we today, and what is our contribution to the variance spectrum for CO2 in the planet? So we got to expand the scale. Here's where we are today at 413 parts per million. And so on this graph, there's the human contribution to the variance spectrum. So we have perturbed the atmosphere on a time scale that is unique and on a magnitude that's consistent with all the other perturbations so far. So we are changing the atmosphere, and the Earth will respond over many time scales. But there are some consequences. And this is probably the part of the talk that may be most meaningful to you, and that is, what are the consequences of the fact that we're at 400 parts per million? And everybody's favorite is temperature. It's a hot day today, but maybe that doesn't matter. So let's see, how are we to think about what role CO2 plays in the atmosphere? So one of the most fundamental concepts in science is the conservation of energy. And in this context, we have the sun producing sunshine, and that sunshine falls on the planet Earth. The planet Earth is also an object. It also has Earthshine, and we radiate back into space. And the conservation of energy says that the amount of energy that falls on the Earth from the sun is matched by the amount of energy emitted by the Earth in terms of Earthshine. And this flux has these particular units, and the amount of flux from the sun onto the Earth goes as the temperature to the 4th power. And our Earthshine into space goes as temperature to the 4th power. The sun is at about 3,000 Kelvin, and the Earth is at about 300 Kelvin. So this is really important, that the Earth is in equilibrium with its environment. So the amount of energy we receive is equal to the amount of energy we emit. So let's take a look at the consequences of that for the atmosphere. So in general, this is how much sunshine comes to the Earth, and about a third of it is reflected right off the Earth, and we never see it on the surface. That means the difference between these two numbers has to be equal to this number for the Earth to be at equilibrium with the sun. And so that's why I put that. And you notice I put a little approximate sign there, because underneath this gray box is a lot of complicated attributes associated with what's going on the surface of the Earth, what's going on with clouds, the enormous exchange of energy between water as a vapor and water as a liquid, and so forth. But this is what I want to call your attention to. Here's Earthshine coming up with this particular set of units. And that Earthshine impinges upon gases in the atmosphere. And if those gases are transparent to Earthshine, it comes right up here. If they're not transparent to Earthshine, they absorb it and bring it back to the planet Earth. So the difference of these two numbers had better be on the order of this one. So there's our so-called greenhouse gas effect. I'm sure Steve probably reacts negatively to this. The word greenhouse is really regrettable because this particular physics is not the same way a greenhouse works in your backyard. But in any case, it's really about the absorption of light, absorption of Earthshine by gases. So I don't know where Percy went to. Where is Percy? Is he around here? So Percy wanted me to mention to you, why is it carbon dioxide is such a potent greenhouse gas? And the answer is because the way the molecule vibrates is uniquely tuned to the Earthshine that comes from the planet. Similarly with methane. And methane is even a stronger absorber of Earthshine than CO2. Nitrogen, the majority of the air in our, majority gas in our atmosphere, does not absorb so much. Water absorbs a lot, but that's we have a lot of water in the atmosphere. So let's see what happens now. So if, for example, we introduce new greenhouse gases, that throws this equation out of balance. And so this process known as radiative forcing occurs, which is to say that introduction of a greenhouse gas takes up radiation from the planet Earth, and then to get this number back to 240, the temperature of the planet goes up. Or if we introduce something to the atmosphere that doesn't absorb Earthshine but reflects sunshine, then we could introduce a cooling of the planet, and we'll come back to geoengineering later. So this is radiative forcing. It's surprising to me that up until 2015, this was a fundamental hypothesis measured on some small scales, but not actually shown to be true for the Earth. And so I'm very excited to report that it was scientists associated with the Lawrence Berkeley Laboratory up here that actually sat down and let's prove this. So what they're going to do is use satellites to measure the incoming and reflected solar radiation, and satellites to measure the Earthshine that comes through the atmosphere. They're largely the infrared cameras. And on the planet Earth, they're going to measure these same quantities, largely with infrared cameras. And then they're going to monitor the changes in the greenhouse gases, and they're going to do this for a decade. That is, every day for a decade, make these measurements and record them. And then finally publish the paper that suggests what is the radiative forcing due to greenhouse gases. And the answer, which was published just in 2015, so here's the radiative forcing that's measured. Here's the CO2 in the atmosphere that's measured. Here's the trend line. And so now we see the direct connection between CO2 in the atmosphere and radiative forcing, which drives the temperature up. So our CO2 waste is the mechanism by which we're warming the planet. There are so many ways to show temperature. This is one of my favorites because it shows places around the world. Blue means it's cooler than the average, and orange means it's warmer than the average. And here's the world graph up here. And we can just take in the meaning of this curve just as we watch. And as probably many of you already know, 4 of the last 5 years have been the warmest on the planet in recorded history. Here's another way of looking at the same data. That is blue. A blue stripe represents cooler than the average for the past 100 years. And a red stripe, and deeper red, means warmer than the average over the past 100 years. So time runs along this axis. Here's the whole planet Earth, and here's the state of California for this same window. And I think the trend is fairly obvious. Many of you have probably heard, oh, there was a treaty or an agreement that we could have signed but didn't that would limit warming to 2 degrees C. That's on the average for the planet. This interesting graph shows the temperature change in the United States as a function of temperature change relative to this average. And you see that there are already regions of the United States that have exceeded a change of 2 degrees C on average. So locally, and in some places it may not have. So locally, climate change or temperature rise is more experienced in some places on the planet than others. This leads to an interesting demographic problem. A recent paper was published in which the United States was polled, do you believe in climate change? And in this region of the United States, the answer was almost certainly no on average. And of course, in these regions, it was higher, which means from a public policy point of view, it's a difficult problem because if you don't experience it, you don't believe it. So there are consequences. How about weather? We've talked about temperature. So the question is, if the average temperature increases slightly, what does that say about the probability for extreme weather? There's a paper I want to show you that's a little bit dated, but it's from our colleague Jim Henson, who's now retired, but at the time he was at NASA. And he asked the question, what is the consequence of a small change in the average on the extreme temperature events? So for example, we could take the average temperature in San Francisco for these 30 years, and we're going to write them all down. There's a nice array of numbers. And we're going to create a graph, as it were a bell curve, the probability that I'll have a particular temperature. And it looks something like what you'd expect from your statistics class in high school. There's an average temperature in downtown San Francisco. The average temperature day-night over a year is 54 Fahrenheit. And of course, there's rare events, right? 3 standard deviations above, 3 standard deviations below. And Jim asked the following question. How much of the Earth has experienced a temperature change larger than 2 or 3 sigma relative to the average? That is, what is the probability of an extreme event? And the reason I like to talk about this paper, even though it's a little bit old now, is because it has one of the most powerful graphical images on the consequences of a small change in the average. So here's the plots. They're color-coded. Purple is 3 standard deviations colder than average, and brown is 3 standard deviations above the average. Okay, 1955. You know, some places are warmer, some are cooler. 1965, some places are warmer and cooler. 1975, some places are warmer and cooler. You ready? So here we are in 2011, which was the last data set used by this particular, by these authors. And it should be now intuitive to you. If you have a distribution and the average changes by little, the effect on the tails is quite large. So one consequence of a warming planet is that extreme hot temperature events are more likely to occur. And I think it's obvious to all of you, since this paper was published in 2012, the number of extreme temperature events continues to rise. This was just published a couple of weeks ago from the country of India, in which they recorded the heat and cold waves as a function of year. So there's less than 50 for 6 years. And then in the past 2 years, the number of extreme events has jumped radically. So there are some consequences: temperature, weather, and perhaps one that might surprise you the most is behavior. So 2 young men are walking down a street on a hot summer day in a small town in Italy, and one of them says to the other, let's go to a pub and get a beer, because if we run into those other guys, we're going to start a fight. Well, Mercutio and Benvolio were walking down the street, and they ran into Thibault and the other gang. Romeo tries to intervene, and of course violence ensues and 2 men wind up dead. And so launches one of Shakespeare's great tragedies. But did Shakespeare have it right? On these hot days, is the mad blood stirring? It seems unreasonable to imagine that on a hot day we're likely to be more violent, because if you go to some parts of the world, I just came from the Middle East this past week where it was 115 degrees and people were not killing each other on the street. But our colleague Solomon Chong here at UC Berkeley and a couple of his graduate students published an extraordinary paper a few years ago that asked the following question. When it's warmer than the average for that region, are you more likely to be violent? And so he looked in this first data set at this region in Africa, the whole sub-Saharan Africa, and then the whole global tropics. So here, for example, is the increase in conflict in this in East Africa, right here, as a function of the temperature deviation from the mean. Now, there's some large shading here, and that the authors are trying to say that's sort of the error bars, because 3 sigma events, or temperature changes that are positive or negative 2 or 3 degrees, are rare. Nevertheless, the trend is pretty obvious, isn't it? A 50% increase in local violence with a temperature rise of about 1 degree. Notice this scale is different. Here's Civil War incidents in sub-Saharan Africa. Here's civil conflict onset in the whole global tropics. Now, regrettably, some of the students in my classes say to me, well, that's true for those people, but it's not true for us. Of course, that's wrong. Here's violent personal crime in the United States. Here's rape in the United States and intergroup retaliation. And you see there's a strong correlation between temperature deviations from the mean and the onset of violence. Now, correlation is not causation. I know that. I know you're thinking the same thing. But law enforcement and defense ministries around the world take climate change very seriously, because the correlation is powerful, as evidenced by the data. Researchers are looking for what are the issues related to causation. That is, if it's 3 degrees above the average temperature your body is used to, are there changes in brain chemistry, for example, that can be documented that would show that? And researchers are looking at that as we speak. So, other consequences: sea levels, glaciers, ice levels. We can run through these quickly. A landmark paper, 2015. Here's the global mean sea level as a function of time. And these authors called attention to something they found very disturbing, which is that for the early part of the century, the sea levels are rising on the order of 1 millimeter a year. But in recent times, it seems to have accelerated to on the order of 3 millimeters a year. And this is surprising. And the community was shocked. And so another set of researchers examined a complementary and the same data set, redid the whole analysis, and concluded they're right. Not only is the rate currently at 3 millimeters a year, but it's accelerating. So why is that happening? Well, of course, sea levels rise as the planet's temperature goes up, because the density of water changes with temperature. So why would that suddenly accelerate? Well, we can look, for example, at the contribution to sea level rise from just the ices that are melting in Antarctica. And here are the data here with the error bars shown here. Ignore these other 3, they're models. So we see already that Antarctica has contributed 6 millimeters to a sea level rise from the ices melting. That is to say, acceleration is happening because not only are the oceans warming, but they're also filling from ice that's melting. What does that mean that sea level rises a few millimeters? I know what you're thinking. You want to fall asleep. This is not really an important issue. But if you look at how the oceans circulate, you'll recognize, for example, in this particular part of the South Pacific, we have warm surface currents come up from underneath deep in the ocean and come up and move across the Pacific. And what that means is that if you measure sea level rise around the planet, it's not uniform. There are some places where the sea level is rising more than others. Believe it or not, the oceans are not a flat bathtub. They actually have different levels for different parts of the world. And I want to call your attention to the fact that this region of the world is experiencing sea level rise much more rapidly than other parts of the world. And that is why, for example, that the Marshall Islands are disappearing. It is one of those vexing sort of ironies of climate change, is that you and I, who have such great wealth, are the slowest to experience sea level rising. And the people who are poorest in the world experience the most rising. Some irony there. Let's take a look at glaciers. Here's the Rhone Glacier. It's in Switzerland. The front of the glacier you can see in this photograph from 2014. It's right up here. There's a mountain pass that goes this way. My daughter and I hiked along this trail along here and took some measurements along that glacier in 2014. And I want to call your attention to these buildings down here at the bottom because in 1850, the glacier, this is an artist sketch, by the way, the glacier was in fact all the way down here at the bottom of this valley, very close to this particular village. The Rhone Glacier is receding. It's receding rapidly. By 2050, the Rhone Glacier is expected to be gone. That means the Rhone River, one of the most important rivers in Europe, will be a seasonal river and not a year-round river. So we have a lot of data on glaciers. Here's the number of glaciers that we have measured. We've measured their mass in one way or another, or we've measured their front. Thousands of glaciers have been measured by scientists. And here's the trend line up to 2010. This dark curve represents all the glaciers. And these jagged lines here represent the data just from 30 so-called famous glaciers. The answer is the glaciers are shrinking, and they're shrinking quickly. Let's take a look at the Arctic ice. Let's go up to the North Pole. This is the Arctic ice in square kilometers as a function of time of year. In the summertime, the ice is retreated the most, and in the late winter, it's at the deepest part. This is the average for those 3 decades. Here we are for 2018, and here's the data from 2019 as of earlier this week. So the ice in the Arctic is receding. Let's go to Antarctica on the South Pole. Each one of these curves, the size of this disk represents how much water has either frozen or melted. Melted if it's orange, and frozen if it's purple. And here's all of Antarctica, and then these are the various stations around this measurement. And this was for this particular decade. You with me? That's decade number 1. Decade number 2. Decade number 3. Decade number 4. The Antarctic is melting. This paper was just published last week, and it shows the rate at which the Antarctic ices are melting as a function of time. So an interesting phenomena is that this rate is oscillating and getting much bigger with time. And you don't have to be a mathematical physicist to know that when oscillations begin to get large, instability is likely to ensue. So here's our summary. Planet's warming, sea levels rising, glaciers retracting, ice retreating, extreme weather increasing. It's our CO2 changing the planet. I could talk for a whole nother hour or more on the biological consequences. I've only talked about the physical consequences. So, what's going to happen in the future? To do the future, we need a mathematical model that allows us to extrapolate in the future. And these mathematical models are difficult. But these equations, which are found in our textbooks, are near and dear to the heart of those who do science and engineering because they tell us about the conservation of momentum and mass and energy, which are fundamental to our understanding of the universe. These equations can be solved on a computer for situations that are quite complicated. If you drove here today in a car made after 1990, that car was designed, the airflow around that car was designed on a computer using these same equations pixelated for the space around a car. And of course, all modern aircraft are designed with the same equations and the same type of computer programs. So why don't we do the same thing? Let's just model the climate of the planet Earth. We just need a lot more pixels, as it were. So here's a picture of the Earth, and I've drawn it up like that. So let's see, we have pixels on the surface of the Earth, and those pixels contain the geography, mountains, valleys, rivers, oceans. And then above them we have voxels, volume elements, and in those volume elements are clouds, or dust, and are all kinds of attributes. And now we're going to solve those equations, and coupling to those equations are all these different physical phenomena, which is to say how the clouds interact with the sun, how much smoke comes from smokestack, aerosols. It is probably the most difficult intellectual challenge of our time to connect all the physical phenomena that are occurring on the planet and in the air to these equations. People are doing it. How good are they? It's difficult to test a mathematical model by making predictions of the future because you're going to be waiting a long time to test them. But what you can do is you can build these models and then you can calculate back in time what should have happened based on the math and compare it to the data. This is where it gets really interesting. So here is temperature of the planet as a function of time. All these gold curves represent different computer groups. The red curve is the average of all those computer groups, and the black line are the data. It's pretty good. The nice thing about a computer model is if you can accurately predict what happened back in time, you can parse the model and say how much of it was due to CO2, how much of it was due to dust, and so forth and so on. So I have a set of graphs that show that for you. Here's a temperature compared to the average between 1880 and 1910. And then this is time along this axis. And what we're going to do is we're going to go back and use these computer models to look at how much did the orbit change between the Earth and the Sun? And how much did the solar output change? And the next one, I believe, is volcanic activity. And you notice there's a couple of big volcanic eruptions that occurred. So let's take all these three natural forces together and compare it to the data. And then let's ask, what about human forces? For example, land use. We do all kinds of things to the land. How about ozone? Turns out we put a lot of ozone, and ozone is a very important greenhouse gas. And then we can take aerosols. We put a lot of aerosols in the atmosphere, and they cool the planet because they reflect sunlight. And of course, we can take a look at methane and CO2 as the predominant greenhouse gases. And now we can compare them to the observed, and I had to rescale, and we can put them all together. Close, not quite as good. So let's take the human factors and the natural factors and combine them all together and compare the data with the computer model. And you see that we're doing a pretty good job of understanding what has happened in the past. Not perfect, pretty good job. Again, it's an extraordinary intellectual challenge that takes the best minds of our generation to go into these models and make them more accurate. So one of I could spend an hour on future predictions, many of the papers published in the literature, and I know you only have limited time. I wanted to show you this one particular model because it demonstrates so well what has in fact been happening. So what happens 25 years from now if we keep the world to a 2°C average? And we're not even close to that. But let's just imagine we did that. And ask, what is the night temperature like, the coldest night temperature? And you see the extraordinary warming, 8°C, occurring in the Arctic and in the Antarctic. The rest of us see the average on the order of 2, which is a poignant reminder that as the planet warms, different parts of the planet get warmer faster. Why does the Arctic get warmer faster? Well, right now it's covered with ice and it reflects a lot of sunlight. As the ice retreats, it exposes rock. Rock absorbs sunlight and heats up more. And so this is one of the reasons why the Arctic is going to warm up sooner. So we have all these things happening, and mathematical models tell us what's going to happen in the future. And all these topics require the best minds going forward. Okay, the Earth has seen this before, even though it wasn't due to humans. Well, let's go back, and now we're going to use shells buried in the bottom of the ocean to ascertain what the temperature of the planet was. The mechanism by which that is discerned is interesting, but really not appropriate in this context. This is the deep ocean temperature going back over 60 million years. And it fluctuates a lot. And what's this bump right here? That's called the Paleocene-Eocene thermal maximum. And it is a puzzle indeed. So what we're going to do is we're going to analyze the seashells that are buried, and we do that the same way we do the ice cores. You dig a hole in the bottom of the ocean, you pull up the mud, and you go through it slice by slice by slice. And we're going to look at the isotopes of carbon and oxygen because they tell us about where the CO2 came from. And here we have, this is 55 million years ago, and here's this massive amount of CO2 and or methane appeared in the atmosphere. Where did that methane or CO2 come from? Unknown. So there are hypotheses, a meteor strike, or a meteor strike in the northern latitudes such that the peats, the carbonaceous soils in the northern latitudes started catching fire. It's not really clear where it came from. Nevertheless, there were consequences. So that was about 4,000 gigatons of carbon into the air. Right now, you and I have dumped in 1,000. This is the temperature. The oxygen isotope is a proxy for temperature. And so you see that you had about a 6 degree C temperature rise, and it lasted on the order of a few 100,000 years. If you look at the shells, there's this window of time in which the oceans were so acidic from that 4,000 gigatons of CO2, the shelled animals all dissolved, and they just weren't present. Again, after about 100,000 years, they recovered. So this mechanism by which the CO2 in the atmosphere is taken up into the soils, into the oceans, into the deep underground, and comes back as volcanism, is at play. And that mechanism has re-equilibrated after a few 100,000 years. So what did the world look like then? Now, caution, 55 million years ago, the continents weren't in the same place they are now because the continents drift. However, it's pretty clear that the average temperature, this is the average day-night temperature over a year in degrees C. Does anybody know what your body temperature is? So in some parts of the planet, you are very, very close to not being able to cool yourself because it's never cool enough to have a temperature difference between the outside and you. And of course, there's no ice. And as a consequence of that, the Amazon basin is underwater. The eastern seaboard is underwater. What we call the Central Valley is, in fact, a lagoon. And certain parts of the world are completely underwater. I just want to remind you that the average temperature in this units, degrees centigrade, is 12 degrees C. So you would be comfortable maybe in Antarctica in this particular setting. So how fast are we changing the atmosphere compared to this PETM event? So this event looks like it's on the order of 1 billion metric tons per year. These are the data from the ice cores, and these are mathematical models. And you see that it's about 3,000 or 4,000 years that this CO2 was introduced in the atmosphere from this process that we don't yet understand. Right now, we're putting 10 billion metric tons of carbon per year into the atmosphere. That is, our rate of dumping carbon into the atmosphere is at least 10 times what it was during this incident that occurred 55 million years ago. So the atmosphere is changing. The change is due to combustion. The climate is changing. Radiative forcing connects that CO2 in the atmosphere to our changing climate. The Earth has seen this before, and in a couple 100,000 years, we'll return back to where we were. Well, that's encouraging. So what can we do? So I'll just close our lecture today by saying that the International Panel for Climate Change and other scientists have some recommendations about what we can do going forward. Technical recommendations. I'm not going to talk about policy today for obvious reasons. An energy-efficient infrastructure, the way we heat and cool our buildings and homes, consumes way too much energy, and we can address that. The United States is reducing the rate at which CO2, the changing rate at which CO2 goes into the atmosphere by replacing coal with natural gas. That's a good idea. I want to remind you, though, that the reason we are doing it is not because of climate change, but because hydraulic fracturing has made the natural gas cheap. And so it's really our wallets that are driving the use of this so-called clean fuel. Hydrogen might be even better. Wind and solar power, I think all of you are aware of how that's emerging. It's really surprising and exciting to someone like me to realize that wind power is now deliverable at 1 or 2 cents a kilowatt hour, which is cheaper than just about anything else you can do. I know it seems trivial to say plant a tree to save the world, and it's sort of a joke maybe among some people, but scientists are emerging with more and more studies about the role of planting trees. And it's not just about the tree. The tree is a living organism that communicates with the soils around it. Soil carbons, fungi, and all these things are stimulated by trees. And it seems pretty well established now that on the order of 1 billion trees, a lot of trees, on the order of 1 billion trees could suck 1/3 of the CO2 that we've put into the atmosphere out of the atmosphere. So there's a movement around the scientific community about planting 1 billion trees. That would be 1 tree for maybe every 1 person on the planet, something like that. it's definitely doable. We all talk about personal consumption. How do I want to say this? Of course, we need to hold each other accountable for how we live. But it is also a false narrative to think that just because you replace your blender with one that's more efficient, that you're going to save the planet, right? What are needed, of course, are laws, and laws that are enforced. But nevertheless, personal consumption is important. What can I say about nuclear power? It's dead on arrival, not because it's a bad idea, but because it's about 10 to 30 times the cost of wind and solar power. So I don't think any investor is going to build a nuclear power plant when they can get 10 times the return or more with wind or solar. I'm going to leave you with these last two. So what are these ideas? The International Panel for Climate Change still holds on to this notion that we can sequester carbon out of the exhaust stack or directly out of the air, compress it, and pump it underground and put it in the places that we've been taking oil and natural gas out of. They still hold that to be one of the foundation principles for dealing with climate change. My particular research and that of several of my colleagues here at Berkeley are on these two schemes. We have been and are developing materials that do this, and they do this as economically as possible, but there is no way that you can take carbon out of something without having to pay for it. And this is why many of us believe that a cost of carbon is the only public policy that's reasonable that will encourage these kinds of activities. So I'd like you to join me in this extraordinary mission. Thank you very much. I'm happy to answer your questions.
pulling CO2 out of the air, producing hydrocarbons, and presumably absorbing energy from the sun to do that. Now, was that just so small an effect that it didn't go into the equilibrium? How does that play into that equilibrium?
Right. So if we think about that equilibrium as tanks moving things around, there's time constant, and the equilibrium is established after a change occurs. But the planet has been warming and cooling due to all kinds of events, including that one. So I wouldn't say that the emergence of photosynthesis was out of equilibrium. It was a new process was established, and a new equilibrium was established, and the planet of the Earth changed.
But I mean, during that time, it absorbed energy from the sun, and some of that went into producing hydrocarbons instead of shining out into space. Is that much correct?
I'm not sure I understand your question. Can you say that again?
When photosynthesis was discovered,
yeah.
and plants started absorbing the sun's energy and producing hydrocarbons, some of that energy went into producing those hydrocarbons.
Absolutely.
And wasn't re-radiated out into space.
Right.
And so during that time, looked at from the outside, the equilibrium was broken. You had energy coming in and you had energy coming out. Is that?
Yeah. Okay, yeah, I'm with you so far. I'm in agreement.
Okay.
And there are consequences for that. A new equilibrium is reestablished. There's radiative forcing that can be positive or negative depending on what attribute is happening. And those numbers, if you notice those numbers, they're very small. They're on the order of a few milliwatts per square meter, whereas we're talking about incoming. So they're small effects. They do change the temperature of the planet, and that probably did happen when the emergence of photosynthesis occurred, although photosynthesis is much more interesting from the point of view of oxygen and so forth and so on, I think so. Let's start with the man in the dark shirt, and I'll come forward and then back.
Can you explain a little bit more what you mean by the radiative forcing? Maybe
not stored. So the Earthshine and the sunshine are balanced to maintain the conservation of energy. That is, the amount of energy that comes onto the planet is matched by that going out of the planet. Always. So what happens then is when something changes on the Earth, whether it's plants or atmosphere or whatever, the amount of Earthshine going out into space might change slightly. And to maintain equilibrium, then the temperature of the planet has to change, because the amount of Earthshine goes as T to the fourth. Remember, that's why I was saying earlier. So when the Earthshine changes, the temperature changes, and we get the two fluxes back at equilibrium to each other. Does that help? Or so
the Earth can't store energy.
Well, it does. There's a heat capacity of the planet, just like there is in a bucket of water. And if you change the temperature, the heat capacity, there's a thermal mass. So there's a time constant. And geological time scales, the Earth is always in equilibrium with the universe, as it were. Okay. Let me just get this. So 1, 2, 3, 4, 5. Okay, go.
The first time I saw that amazing relationship between oxygen and carbon dioxide, I never even heard of that. And I'm amazed that it works that way. Is there no effect with photosynthesis? If you increase carbon dioxide, and the question is, plants make the oxygen. That's where I think that's maybe where it comes from.
Yeah.
And so did you ever take that into account? And then sort of a related question is, what happens to all the stuff that's stored up in the tundra that now all the way from the atmosphere? You didn't mention, I guess that part of the whole biological thing.
Well, let me try those two in a row.
Was the oxygen simply because of, yes, you burn carbon dioxide, you use up oxygen?
Right. So if you look at Keeler, the Sun Keeler's papers, right? So what he had to do was figure out where the oxygen and the carbon are coming from and going to. That was the real intellectual genius of his work. And to do that, the biggest effect was the amount of CO2 in the air was much lower than the amount that should have been because of what we burned. And so then it was realizing that, of course, the oceans take it up, plants take it up. So that was the first key step. Then the question is whether the oxygen matched that value, but of course photosynthesis was taken into account because he'd already done it for the carbon, so he had to do it for the oxygen too. Does that make? And the second question was the piece. So that was that.
I don't know how much is stored in the tundra, but it's in fact a lot.
Huge.
And if that all burns, like half or something.
That's the PETM idea. That's where it came from. It took 4,000 years, but. This one was next.
How do we balance our agricultural land so that we can eat and planting enough trees out in?
On a micro scale, Marin County has done this experiment where they've looked at if I change the way I till soils in agriculture, how much more carbon can be stored in the soils. And it turns out to be a phenomenally effective tool. If we change the way we do tillage and change the way in which we manage our farms, farms aren't a problem. Farms actually become an asset because the soils are taking up carbon from the air. And so that's a big contribution that Marin County has made. And now the International Panel for Climate Change is calling for a worldwide reconsideration of farming. Not reducing farming, not getting rid of farm, but in fact managing our soils to think about them as a carbon sponge and not just something to move around that has nutrition for the plant.
Well, my primary question is just in terms of square acres. How many square acres do you need for building trees, and how many square acres do you need planting corn and so we can eat wheat so that we can actually feed ourselves? I mean, isn't there a battle going on between our need for nutrition and our need to scrub the CO2?
Yeah, a battle is too strong a word. Let's just say stewardship needs to be considered carefully. From what I've read and heard, the bigger conflict is the use of biomass for fuel. So if we want to replace oil with biomass that is things that come from trees and plants and grasses, that's where the food fuel conflict is biggest. the plant a tree versus food is not seen as a conflict, but as one of stewardship. And so there are large portions of farms where that aren't being used for crops, that are just tilled dry, and they could be planted with short-term crops that would bring carbon into the soil, for example. Let's see, it was this way, and then it was up here.
Yes.
Yeah.
So you talked a little bit about how solar and wind were becoming economical and truly much cheaper than actually fossil fuel sources of energy. But they're temporal, of course. Can you talk a little bit about the ways that we can store electrical energy, and then also talk a little bit about how does California environmental policy actually limit things like pump hydro and even wind, and maybe we should be trying to tweak California environmental policy?
Well, we certainly should be tweaking California environmental laws, but to go back to the first part of your question, intermittent sources lead us to the primary energy challenge of our generation, which is storage. So the fact that the wind doesn't always blow and the sun doesn't always shine is in fact a problem, and there are calculations about what the consequences would be for consumers when we had no storage. And the answer is it won't work. So we need to think about storage. So ways to storage, well, one way people talk about is batteries. Batteries are expensive. Batteries cost a lot of CO2 to produce. Batteries have a lifetime. We don't currently steward dead batteries very well, with the possible exception of lead-acid batteries. So it's possible. Another way to store energy is to pump water uphill. We do that in California already. That is, you pump water up to the top of a reservoir, and then when you need water, you pump it down. If you've ever been to the Pitt River, for example, in California, that's an example of that. You can store energy by pumping gas into a cavern under pressure, and then when you need that power back again, you just release the gas through a turbine. That's been experimented with, and it seems like for some kinds of cavities, salt caverns in particular, that might be effective. Right now, we're not pursuing any of those at the level necessary to make a complete transition to renewables. I think I'm answering your question, aren't I? You look really unhappy.
Yeah. So I actually heard some LBL research scientists talk about this, and they claim that actually pump hydro could be expanded much more rapidly than it is currently, and part of the problem is actually environmental regulation limiting it actually.
It's certainly true that we have created laws, especially in California, about hydroelectricity that were motivated by environmental concerns, when I was a boy, a long time ago. And maybe we need to rethink those. So, for example, microhydro, which is to say any stream or river can produce a few kilowatts, maybe a megawatt of power, and if you distribute those around California, you wind up generating a lot of electricity. But the laws that apply for building a mega dam are the same that apply for microhydro. And so, maybe it's time to reconsider that. But creating another Hetch Hetchy, for example, is another environmental battle, discussion, conversation, and I'm not sure that's a good solution either. So I don't have an answer to your question, but you're quite right. Hydro storage, pumping water uphill, is a good idea, and that's a conversation we have to have as a community about the balance between storing our energy and preserving natural environments. Does that make sense?
Yeah.
Okay, we need some more hands. How about 1, 2, 3? Oh, 1, 2. What's that? I'm sorry. Okay, all right. Your next one. Sorry. That's hard to keep track. So many exciting questions, sir.
So it seems to me, based on your early part of your presentation, that fossil fuel-based generation of electricity is one of the largest contributors to existing carbon dioxide presence in the atmosphere. The second point is, I believe that technological change can be done much faster than social engineering, such as redesigning cities, getting people to drive less, or change a lot
Yeah, I can give you some numbers. So with the technology that exists in the middle to latter part of the 20th century to capture CO2 from power plants is a 1/3 increase in your electricity bill.
For total elimination?
Yeah, 90% elimination. So that's a lot. And policymakers and power plant owners haven't done it. Too much money. So that's why many of us, including myself, are actively involved in research and ideas for trying to drop that. However, you can estimate a theoretical limit because you're really unmixing a gas. And the science of thermodynamics tells us energy cost to unmix a gas ideally. And that is 10% of your power bill. So even if we had some magic machine that it was at the thermodynamic limit, your power bill goes up 10% to get rid of 90% of the CO2. So we're shooting for that window in between. We're not going to make 10%. But I would say between adsorption, absorption, and membranes, the three major technologies for capturing CO2, we're probably on the order of 20% now. But there's no policy to implement it. And in the absence of a policy, no power plant owner is going to spend money to reduce their CO2 emissions. Right? That's the way, right? You know that as well as I. So the major challenge is for you and I to vote for people who are informed by science. They can be Republicans or Democrats, doesn't matter. If they're informed by science, they're the people we want to talk to about creating policies which would allow for power plant owners, for example, to retrofit with this process. Does that make sense? Okay, let's see. 1, 2, 3, 4. Can we do that? Can you remember your numbers? Great, yeah. Sandy. Thank you for saying that. Yes, thank you for mentioning that. Yeah, I'll repeat the question. So the question was, what about the geoengineers, excuse me, who have ideas for how to manage in a relatively short time scale the changing consequences of CO2? So an obvious one that maybe you've heard of. Let's put a satellite out in space and put up a big umbrella and reduce the amount of sunshine, and therefore the amount of Earthshine will go down because the temperature of the planet will drop. Okay? Really clever idea. It might work. It would be phenomenally expensive and an engineering project of extraordinary magnitude. The one issue, though, is that that kind of intervention may help with temperature, but CO2 has other consequences in the atmosphere. I didn't talk at all about biology, but I did mention that in the PETM event, all the seashells dissolved in the oceans because of the acidification of water. So CO2 in the atmosphere has other consequences besides temperature, and they're mainly ecological and biological. So that kind of geoengineering wouldn't intervene. Other kinds of geoengineering, which Bill Gates called for last week, if you were watching the news, is let's spend $1 trillion and get hyper-capitalism involved. We can build walls, we can build infrastructures, and the wealthy people of the world will be protected from the consequences of climate change. And the people in Bangladesh, well, yeah, it's hard. So there are other geoengineering schemes. I'm not thinking of them off the top of my head. Those are the two others. Oh, introducing aerosols. That's the other one. Thank you. I was just in the Middle East, and they were telling me that Abu Dhabi is spraying aerosols from aircraft to actually produce rainfall. But the physics is the same. Once you have aerosols like a volcanic eruption, you decrease the temperature of the planet by changing radiative forcing. Again, just like putting a sunshade up, that may create rain and it may make the planet cooler, but it won't mitigate the effects of CO2. Manipulating weather may also be occurring elsewhere, but that doesn't address climate change. It's a local thing if it's happening locally. Yeah, Clay?
The IPCC calculations you showed for assuming 2-degree rise in temperature. What happens if we do that?
So that's a great question. So the question was, I showed this graph that showed the consequences of an average 2-degree planet in 25 years. We are nowhere near on track for a 2-degree planet. We are right now 1.5 degrees, but as I showed the map of the United States, there are regions that experience more. When I first started getting involved in this research, IPCC does a report every couple of years. The early reports were predicting what would happen to CO2 and warming if we did nothing. And if you look at those predictions from 2012, we are above them. That is to say, we are warming and introducing CO2 more rapidly than the worst case scenario from 2012.
So what's the consequences of those temperature shifts?
Well, they're only going to be worse. Right. Actually, let's see, you were next. Hang on just one second. If you know a farmer, ask them about climate change. Anybody who lives close to the land for more than a decade or so will be able to tell you experientially what's going on because they see it and they live it. Yes, ma'am, please.
That's actually kind of related to that. What is your response to people that say we're past the point of no return?
I'm reliving a moment when I was a boy, and Rachel Carson published this book. Maybe some of you have heard of it, called Silent Spring. And I remember at that time the same kind of discussion, right? We're at the end. And technology put that off for a little bit, and maybe other things are driving us to the end than what Rachel was talking about. And I'm the kind of person who believes that we can do this. I remain an optimist. I believe that people will make the right decision. There are powers and principalities that seem to interfere. That frustrates me a great deal. But I think we can do this. What's particularly sad for me, I mentioned Bangladesh earlier, and I want to come back to that. It's particularly sad for me that probably my children and I will be fine because we're wealthy enough to mitigate. You know, if the Antarctic and Greenland melt, it's 16 meters of sea level rise. That puts the Berkeley campus sort of at the water's edge. Elevation 66 is a popular pub in El Cerrito, near where I live. So that turns out to be a beachfront property, and my home is fine. And many Berkeley people living up in the hills will be fine. It's this notion about the part of the world where people live on $1 a day, 1 billion people. 5 billion people who live on $3 a day. What is our responsibility there? Because the United States and China have contributed most of the CO2 in the atmosphere. Do we have a responsibility there? I believe we do, and that's where I'm really vexed. I'm sorry I can't really answer your question. How about 1, 2? Okay, can you hang on one time? Yes, in the back.
Yeah, but everybody breathes the same air, and we all metabolize oxygen, not CO2, not methane. When does the atmosphere become unbreathable?
That's a great question. Let me just think about this, because I had this conversation with some people from the Navy, because, of course, the Navy worries about this in their submarines, and NASA worries about it for their astronauts. And I believe the answer is 4%. And so we'd have to burn a lot more. We probably cannot burn enough carbon to have the atmosphere such that we start to die from asphyxiation. 4% of the law. However, to get to your point, that's if you die. There are effects of CO2 at much, much lower concentrations. And people are starting to look into this. And there's a discussion now of 1,000 or 2,000 ppm affecting cognition. And 1,000 or 2,000 ppm we could get to. So, yes, sir.
That was going to be my question. Are we producing oxygen enough?
No, oxygen's fine. That's 20% of the atmosphere. We're okay with oxygen. 1, 2. Yes, sir.
It looks like we're going to have a lot of droughts, obviously, with these changes.
plants, research in C3 plants being converted into C4 plants that are better in, or at least have less consequences of photorespiration, particularly because what's going to happen with droughts is there's going to be food insecurity, which leads to, as your chart was showing, violence and other consequences, obviously. When there's food insecurity, a lot of bad things happen, right? People start to steal and start wars and so forth. So have you heard anything about the C3, C4?
I don't know anything about that. I'm sorry. You probably know more than I do. I do know a little bit about algae production, which is the notion that if we put algae in the oceans, it'll suck up CO2 with a biological pump and then die and sink to the bottom of the oceans, and that's how we pull CO2 out of the atmosphere. And people have actually, in some cases illegally, tested such schemes. The difficulty becomes that whenever you grow a biological object, right, it needs resources. And the algae needs iron, and then it needs nitrogen, and then it needs phosphorus. And to get the scale of CO2 vacuuming with algae at scale, you wind up delivering to the ocean or to the pond or whatever, minerals that you churned up from some other place and trucked across the country and then put in the water, and you wind up generating as much CO2 as you capture with the algae. So the algae capture idea, in the absence of a big technological breakthrough, is not likely to happen. But no, I'm unaware of the C3, C4, and maybe you can tell me a bit. There was another question. Yes, ma'am.
I really have two questions. Can you say any more about why certain parts of the Earth, of course interested in the Western United States, are warming more than others? And in my little world, people talk a lot about possibilities for, as you say, carbon farming, blue carbon rebuilding wetlands such as the Delta. Do you use trees or other kinds of planting as a sort of figure of speech, the most visible thing, or is there something really better about trees?
The answer is both. I use them as a figure of speech for all things that we can plant and grow. But I also mean that quite a few researchers are particularly focused on trees and particular kinds of trees because they enable fungi growth in the soils. And the fungi take up, it turns out, a lot more CO2 than the tree ever does. Not all trees do that, but some trees do that. And so this science is really, the so-called rhizosphere, this region around the roots, is a really interesting challenge, and we don't really know enough about it. So yes, both figuratively and literally. Why do some regions warm quicker than others? I don't know the answer to all of that, but the answer that's clear is that wherever there's normally ice and snow, that reflects a lot of sunlight. When that ice and snow goes away, or the time that it's there is shorter, the land absorbs a lot more energy and that warms up quicker. So I think Steve is telling me I get it.
Fascinating questions. I want to thank both the media, the folks back there who videoed all that salt and that salt that will be available online if you want to check out some of the details. Again, we're hoping to continue to record these salts going forward, and of course I want to thank you again.
Thank you, Steve. Thank you very much. Thank you for coming. Thank you very much.